Hello, welcome everyone. In today's lecture, we are going to look at a new concept again, which is called as the effective mass of beams. Previously, we have looked at the effective stiffness of beams, so it is kind of a related concept. And again, the reason for doing this is that we can reduce a continuous system like a beam into a discrete system, and then essentially we can use the single degree of freedom system equations that we have derived to actually look at the vibrations. Okay? So by the end of this lecture, what you will be prepared to do is determine the effective mass of a simply supported beam that is subjected to a vertical force at its midpoint. Again, this might look very specific, but the concepts or the procedures that you will be employing for doing this particular problem is actually something that you can use for a wide variety of problems. Okay, so now let's again kind of recapitulate why we want to calculate the effective mass. Again, this is something that we have discussed before. The first important thing is that beams are continuous system. Essentially, you can think of them as infinite degree of freedom systems. But in some cases, under some assumptions, you can essentially reduce this infinite degree of freedom system to a single degree of freedom system. And then to do that, essentially you have to find out what is the effective stiffness and effective mass of the system. And that is the reason why we are trying to find out the effective mass and effective stiffness. Okay? And once you do that, essentially you can replace this continuous beam essentially as a spring mass damper systems that you have looked at many times, right? And essentially analyze the vibrations using that. Okay, so if you have this as the displacement, right? So essentially you replace the mass by an effective mass, the stiffness by an effective stiffness, and then the damping constant usually by a C effective. Okay. Of course, we won't be like usually calculating C effective because mostly it is experimentally determined. Effectively, you want to take a system like a beam that is continuous and has different displacements at different points and essentially reduce it to a system like that, okay, which we know how to analyze. Okay, that is the point of finding out the effective mass. Okay. Now we are going to look at a very specific example today, but that example can be generalized for other cases also. Okay. Now let's think about what an effective mass means. Now if you go back and recall what we did for the effective stiffness of a beam, we said that the effective stiffness is determined with respect to a specific location and for a specific direction. Okay? So the effective mass is also similar in that way. It is defined with respect to the velocity at a specific location. So velocity already has the direction built into it. So in some sense, the effective mass is also defined for a specific location and a specific velocity. Okay? It is not something that you can define arbitrarily. Okay? So that is something that you must keep in mind. The other thing that I want to note is that this effective mass is one way of describing this parameter, but it's often also called as an equivalent mass or a lumped mass. Okay? These are concepts that are actually widely used in mechanical engineering. So even in something like heat transfer, you actually use something called a lumped mass to analyze some systems. So essentially, what you are doing is you take a distributed mass and then effectively treat it as a point mass. That is what you are doing. Okay? And the basic idea by which we obtain this effective mass is essentially equating the kinetic energy of the total structure, a beam in this case, to essentially m effective v squared by 2. So if you think about kinetic energy is usually given by half mv squared, right? So essentially, that m is replaced by this m effective, and this v is the velocity at a specific point. Okay, so essentially we find out what is the total kinetic energy of the structure, and then we equate that to essentially half m effective times v square, where v is the velocity at a specific location. Okay? At a specific location. Okay, so when you look at the example, these things will become a little bit more obvious. Okay, so what you're going to look at is a simply supported beam, and this is a specific case that you're looking at where you essentially have this beam, okay, and then you have a force that is acting at the midpoint, and that is the force that is causing this vibration. And this force is in the y direction, and the span of the beam is in the x direction. Okay, so as you apply this force Fy of t on the beam is going to move up and down. Okay, and we are interested in finding out what is the effective mass of this beam as it undergoes this vibration in the y direction. Okay, for that we have to assume a few things, or we have to actually know some parameters. The first thing is what is the cross-sectional area of this beam. Okay, what is the bending rigidity, which is the Young's modulus time the moment of inertia of the beam, the area moment of inertia, and what is rho, which is the mass density of the beam, and the length of the beam. Okay, so if you know these parameters, we can calculate what is the effective mass of this beam for this particular situation, where a force is applied at the center of the beam and it oscillates it in the y direction up and down. Okay, so this is your x, and that essentially is your y. Okay, now to calculate what is the equivalent mass, we have to define the equivalent mass with respect to a specific velocity. So what we are going to do is we are going to take that velocity v to be the velocity of the beam at the midpoint. Okay, that is x equal to L over 2. Okay, again, this mass, effective mass of this beam, we are defining with respect to a specific location, which is x equal to L over 2. And essentially, the mass or the velocity that we are going to use for defining the effective mass is the velocity of the beam at that midpoint. Okay, so you can think of this beam as it oscillates. It's essentially going to kind of go like this. It's going to go like that. And then at some point, actually, I made a mistake there in terms of the slopes. The slope is not 0. It kind of goes like this as it vibrates. And then at some other location, it kind of goes like this. Then it changes shape. It goes like that. And then eventually, it reaches the maximum in the other direction. Okay. So at each point in time, the beam is going to have either this shape or that shape or that shape or that shape. Okay. Essentially, it's a continuous variation in shape. And at each point, there is going to be a velocity of every point along the x-axis in the y direction. So every point in the beam is going to have a velocity in the y direction. Sometimes it might be 0 when it is at the extremes, and it's going to be maximum when the beam is at the neutral position. Okay? So y of x is the displacement at any point in the beam as a function of x, and y dot of x, the derivative of y with respect to time, is essentially the velocity of that point in the y direction. Okay? Now we are looking at the velocity at a specific location, okay, and that velocity is v, and that velocity is defined at the midpoint of the beam, which is here. Okay? So that is how we set up the problem. And given this particular configuration, how are you going to find out the equivalent mass of the beam? Okay? And that's what we're going to find out next. Okay. Now, if you want to first find out what the equivalent mass of this beam is, we have to be able to calculate the kinetic energy of the beam. Okay? Which means that we need to know the velocity at every point in the beam. Okay? Now, how do you find out what the velocity at every point in the beam is? That is where our knowledge of strength of materials or mechanics of materials actually comes into play. Okay? We know that when you have a simply supported beam like this, and then you apply a force P at the midpoint, okay, the deflection in the y direction is given by that particular equation. Y of x is going to be P times x times 3L square minus 4x square divided by 40 ATI. Okay? And this is the function for y of x, which is the deflection at any point x for 0 less than x less than L over 2. Okay? For x greater than L over 2 to L, it is going to be a slightly different function, but fortunately we won't have to use it. Okay? All we need is the deflection of the beam for half its span. Okay. Now, given that this is the deflection of the beam, we can find out that the deflection is maximum at x equal to L over 2. So L is the length of the beam, and at some midpoint, you have the maximum deflection. And that y max is given by PL cube over 40 ATI. Okay, this is something, again, you can derive using energy methods or Castigliano's theorem, or you can just look it up in some tables. Okay. Now, if this particular point is going to have the maximum displacement, it also makes sense that this particular point is going to have the maximum velocity. Okay, because that is the point that is getting displaced the most. Okay, so and since the beam is continuous, the midpoint is essentially going to have the maximum velocity. So the maximum velocity is given by y dot max, where y dot is nothing but dy over dt. Okay, so this velocity v, with regard to which we are defining the effective mass, is essentially dy over dt at x equal to L over 2. Okay, that is something that you must keep in mind. Okay, now essentially we want to find out what is the total kinetic energy of the beam, and then effectively equate it to half m effective times v square. That should be equal to your Ke. Okay, so if you know your Ke, okay, then if you know your v, then your m effective is defined. Okay, that is what you're trying to do. Okay, now how do you find out the kinetic energy of the beam? Okay, the kinetic energy of the beam is nothing but half times the integral over the mass of the beam times integral of dm times y dot square over the mass of the beam. So what do I mean by that? So let's say that you have a beam, like the simply supported beam. Okay, and then at some point in time, let's say the beam has, let me just draw this a little bit more precisely. Let's say the beam has this configuration, okay, as it is vibrating. Okay, so this is at some time instant t. Now, at the next time instant, the beam is going to become slightly different. It might, in this case, let's say it's going up now. So the beam is going to kind of look like, again, I'm exaggerating the displacements. The beam is going to look like that. Okay. Now, what you're going to see is that this point here has moved a lot. Okay, whereas a point somewhere here has moved less. So each of these points in the beam is going to have a different velocity. Okay, so you can't just say that it's a mass times some velocity squared divided by 2 is the kinetic energy, because each point mass or each infinitesimal mass in the beam has a different velocity. Okay, so now we can be a little bit more careful. I can say that this particular small segment here, okay, let's say that has a mass dm1. Okay, and there's another small mass here that has a mass dm2. Okay, now for this particular instant, I can say that the velocity of this mass is y1 dot. Okay, and the velocity of this mass is y2 dot. Each of this y1 dot and y2 dot, they are different. Okay, but I can get or define a small enough mass so that within that particular mass, I can say that the velocity is the same. Okay, now I take all these masses, so dm1, and multiply that by y1 dot square and divided by 2. That is the kinetic energy of this small mass dm1. Similarly, I can say dm2 times y2 dot square divided by 2 is the kinetic energy of this small mass dm2. Okay, so now what I can do is I can do this for every infinitesimally small mass inside the beam, add them all up, and that is going to be my total kinetic energy of the beam. So that essentially is what this expression represents. So essentially you are taking dm and multiplying it by the particular velocity at that point, which is y dot, you square that and divide by 2. And you do this for every small infinitesimal mass within the beam, and that's how you get the kinetic energy of the beam. Okay. Now, this dm can be written in a slightly different way. I can say that this dm is the density of the beam, the mass density of the beam, multiplied by an extremely small volume. Okay, that is what this dv is. This small v is the volume, okay, not velocity. Okay, so I can say dm is rho times dv, right? Now what is this dv? Okay, this dv is nothing but the cross-sectional area of the beam times the small distance. Let me just draw this again. I'll just show a single small mass here. Okay, let's say I define my mass like that. That is my dm. Okay, sorry, that is my dm. Okay, this mass is nothing but rho times the volume of that segment. And that volume of the segment is essentially, if you think of this length as dx, the volume is nothing but the cross-sectional area A times dx. That is going to be my dv. Okay, so that is exactly what I have done here. So what I have done is I have taken this dv and then said that it is going to be A times dx. Okay, now my volume integral essentially becomes a one-dimensional integral. Essentially it becomes the integral over the length of x, which is 0 to L, and I can take out this A outside the integral because the cross-sectional area is constant across x for the beam. So I can take out rho, which is the mass density, which is also constant, and A outside the integral, and I end up with an integral which is nothing but 0 to L of y dot square dx. Okay, that is where we end up. Okay, now if you do this further, what I can do is that I can make another simplification. Okay, so if you think of this simply supported beam, okay, in this case, for example, if you look at the left half of the beam and the right half of the beam, they're identical. So instead of trying to calculate the energy for the whole beam, what I can do is I can calculate the kinetic energy for half of the beam and then multiply it by 2, which is going to give me the energy of the whole beam. That is exactly what I have done here. So I have taken this integral, which is the integral from 0 to L of y dot squared dx, and I have multiplied that by 2, but changed the limits from L to L over 2. Okay, so it becomes rho A, the integral from 0 to L over 2 of y dot squared dx. Okay, and why am I doing that? Because I know what is the deflection y as a function of x from 0 to L over 2. That is what we saw here, right? If you remember, this expression is valid only from 0 to L over 2. Now, if I know y of x from 0 to L over 2, I can also find y dot of x from 0 to L over 2. And that is all I need to find out that integral. Okay, and that is the reason why we use this trick. Okay, now once we have that, effectively the kinetic energy of the beam is rho A times integral 0 to L over 2 y dot squared dx. Okay, that is equation number 1. Okay, now what we are going to do is we are going to use the fact that we know what y of x is already. Okay, this is something that we already know. We know that y max is this much. Okay, so using these two expressions, I can write y of x in a slightly different form. Okay, y of x is going to be y max of x divided by L cube times x times 3L square minus 4x. This is just some algebraic manipulation. Okay, the reason that I'm doing this is because if I know what y of x in terms of y max of x, okay, or y of x in terms of y max, then I can also find y dot as a function of y dot max. Okay, so if I take the derivative with respect to time, x is just a variable that denotes the length of the beam. So y dot of x is going to be y dot max divided by L cube times x times 3L square minus 4x square. Now we have something very interesting because this y dot max is nothing but the velocity v at the center of the beam. Okay, we are trying to define our effective mass with respect to the velocity at the center of the beam. Now what I have done is I have written the velocity at any point in the beam as the velocity in terms of the velocity at the middle of the beam. And now if I integrate this expression, I am going to get a v square. Okay, when I try to use the kinetic energy expression, I'm going to get a v square. Then my v square is going to actually cancel off. and my effective mass will only depend on the mass of the beam. Okay, so again, I'm not going to go through all these calculations. What you essentially want to do is you want to take this expression for y dot, okay, which is expression number 2, and essentially substitute that into this expression, which is expression number 1, okay, and then just do the integration. It's just a lot of algebra, but if you end up doing that algebra, what you will find out is that the kinetic energy of the beam will end up with an expression like this, okay, where v is the velocity at the center of the beam. Okay, now this term here, rho al, is nothing but the mass of the beam, because A times L is the volume of the beam and rho is the mass density. So the mass density times the volume is nothing but the mass of the beam, which is mv. Okay, so essentially you end up with an expression that is like 17 by 70 times mb times v square. Okay, so we always, to find out the kinetic energy, to find the effective mass, we effectively equate the kinetic energy of the beam to half m effective v square. Okay, so that is what I have done here. So half m effective v square is 17 by 70 mb times v square. That is the kinetic energy of the beam. Now, the interesting thing or the useful thing here is that this velocity gets cancelled off. Okay, so your effective mass of the beam, as it should be, depends only on the mass of the beam. Okay, it doesn't depend on the velocity, which it should not. Similarly, if you think about our effective stiffness, we showed that the effective stiffness does not depend on the force. Similarly, the effective mass of the beam does not depend on the velocity. The effective mass depends only on the mass of the beam. Of course, you have this weird factor 17 on 35 in front of it, because not every point in the body or not every point in the beam is moving at the same velocity. Some are moving very slowly, some are moving very fast, and some are not moving at all. If you think about the supports, there's no motion at all in the y direction. Okay, so this 17 by 35 factor comes in because the velocity at the middle of the beam is maximum and the velocity elsewhere is lower. But the main point is that we have now essentially approximated by this beam by an m effective, which is 17 by 35 times mb. Okay, now if you go and look back at one of our previous lectures, when we had a simply supported beam that was subjected to a force at the middle, we found that the effective stiffness of this beam is 48 EI over L cube. Okay, so now if you want to analyze the vibrations of such a simply supported beam, essentially you can take this beam and then represent it as a mass that is equal to 17 by 35 mb and a spring that has an effective stiffness of 48 EI over L cube, and essentially you can run the same analysis that you did for the single degree of freedom system, and that essentially will provide you what is going to be the displacement of this or the vibrations of this particular simply supported beam, even though it is a continuous system. Right? So effectively every point in this beam is going to have a different velocity, but we can still analyze it as if it is a discrete mass that has a discrete stiffness, and if you want to include the damping, you can include the damping also. Right? So that is the point of finding this effective mass and effective stiffness. You can reduce a fairly complicated infinite degree of freedom system into a discrete system which has only one degree of freedom and has an effective mass and an effective stiffness. Okay, so in the subsequent classes, we will look at examples of how we can actually use this concept to look at or analyze the vibrations of beam-like structures. Okay, with that, I will conclude and I will see you in the next lecture. Thank you.